Imagine a postage stamp-sized spacecraft, weighing exactly 1 gram, tearing through the Alpha Centauri star system at 20% the speed of light. This tiny probe has already completed its primary science mission, snapping images of distant planets. Now it faces its most difficult physical constraint, sending that data across 4 light-years of empty space. Surviving a decades-long interstellar flight is a significant engineering feat, but it yields zero scientific return if the spacecraft cannot lock onto Earth and deliver its payload. The planned communication link relies on a 100-watt laser on the sailcraft, aiming precisely at a 30-meter receiver telescope back on Earth. At a distance of 25 trillion miles, the laser beam diffuses significantly. By the time it reaches our solar system, the connection operates in a photon-starved regime, where only 288 signal photons per second survive to hit the detector. Under perfectly ideal conditions, those surviving photons translate to a raw data rate of somewhere between 260 bits and 1.5 kilobits per second. This chart shows light transmission across the vacuum wavelength. The blue dips represent molecular absorption in Earth's atmosphere. To isolate the faint laser signal from Alpha Centauri's glare, the telescope uses narrow-band filters to look specifically through these clear windows. With a signal this faint, there is no margin for error. The slightest mechanical misalignment on the sailcraft will instantly sever the link, making microscopic precision the primary requirement for the mission. Even the most tightly focused laser beam naturally expands outward as it travels. Over an interstellar distance, a narrow beam emitted by the probe spreads into a circular footprint millions of miles wide by the time it reaches Earth. The first major threat is pointing bias, a steady misalignment caused by spacecraft warping from thermal or mechanical stress. Over vast distances, a microscopic angular shift at the source translates to the beam missing Earth by millions of miles. As the beam drifts off target, the receiver catches fewer and fewer of those 288 photons, bleeding away the link margin until the connection drops entirely. Even if engineers design a rigid sailcraft with zero thermal bias, the target itself is actively moving through space, introducing a second layer of complexity. Light travels fast, but space is larger. The data beam fired by the sailcraft will take over 4 years to cross the gap to our solar system. This creates point-ahead error. The spacecraft must aim at the empty space where Earth will be in 4.24 years. If it miscalculates orbital velocity, the beam arrives where Earth used to be, missing the receiver. The onboard computer must perform predictive celestial mechanics autonomously. Without real-time corrections from mission control, this adds immense computational pressure to a payload that weighs less than a paperclip. The third and most chaotic error is jitter. This is caused by high-frequency microvibrations generated by the spacecraft's own internal operations, like power distribution or mechanical actuators. Unlike a steady thermal bias, jitter causes the laser beam to vibrate rapidly and unpredictably off the target. This graph displays sharp downward spikes in signal transmission, representing pointing-induced fades, or PIF. A PIF occurs when rapid mechanical vibrations temporarily push the laser beam completely off the receiving telescope, causing massive spikes in bit errors. These microvibrations fragment the data stream, causing bit errors to spike so rapidly that the underlying message becomes impossible to reconstruct. In a real mission scenario, bias, point-ahead error, and jitter are acting simultaneously on the laser transmitter. If the internal vibrations shake the craft, while thermal warping pulls the beam off of its predictive target, the last of those 288 photons scatter into the void. The Earth receiver's count drops to 0. Without a perfectly maintained optical signal, a multi-decade interstellar journey ends in permanent silence. To prevent this outage, the Starshot payload requires laboratory-grade vibration isolation, precise star trackers, and active beam stabilization. If these systems work in harmony, the stabilized beam cuts through the interstellar noise, securely anchoring to Earth to deliver the first images of an exoplanet. To understand the stability required, engineers use the Hubble Space Telescope as a benchmark. The Starshot probe must maintain a line of sight with that level of pointing stability, while flying at 20% the speed of light. Mastering this mechanical precision is a binary threshold. Without it, the data remains trapped on a gram of silicon 4 light-years away. With it, we establish a viable data bridge to another star system.